So thank you everyone for joining me to the last slot. Well done on making it to the end of the full day. I'm going to be talking about Bloom filters today, which is a probabilistic data structure. And I'll explain what that means as we go through. But it's kind of a talk of two halves. The first half is about how I ended up with so much data that I simply didn't know what to do with it. And then the second half is about how I managed to handle that and process it in an efficient way. So in 2013, I started working on a little idea that I had to build a website to process security telemetry. Modern web browsers are packed with features where they can send you feedback on things that are happening in the page. Now, one of the things that they can send you feedback in is when bad stuff happens. And bad stuff might look like this. So this is something that we know within the security industry as cross-site scripting. And it basically means you ended up with some JavaScript on your page that shouldn't be there. Now, if I gave all of you this script tag and said, like, hey, do you want this script tag to run on your site? Do you want it to be on your page? Would anyone say yes? Right, like we all have the context to look at this and be like, evil.com, keylogger.js. Like, I probably don't want this to be there. But an attacker with some kind of evil intentions might have a very good reason that they want to get it there. And we've seen some really kind of almost famous examples of when attackers have managed to do this throughout recent history. One of the most notable ones was something called CoinHive. Now, CoinHive started out as a legitimate idea. And the idea was that we don't like adverts on websites, we don't like the privacy implications, the tracking, they're really, really heavy, they slow down the page, they consume loads of bandwidth. And CoinHive was like, okay, we had an idea. You can get rid of all the ads, but we still need to make some money from our site. So what you could do is you could put this little JavaScript library on the page. And when users visit your site, and obviously the page is running in their browser, we will mine a little bit of cryptocurrency in JavaScript. And that would be the air quote payment that would replace advertising. So there's no more advertising, no more privacy, no more bandwidth consumption. I'm just going to borrow a few little CPU cycles from you whilst you're reading my articles, and that will be how we fund everything. Now, you know, I'm a little bit torn on whether that's a good idea or not from the outset, but the problem was when we have nice things, bad people do bad things with them. And what the attackers realized was like, hey, if I take the library and I put it on your site, all of your visitors will mine cryptocurrency for me. So we now had like some really good incentives for you to find ways to get JavaScript into other people's websites that shouldn't be there. And this became known as cryptojacking. And we went through, especially with the kind of explosion of cryptocurrencies and their popularity, we went through this huge phase where cryptojacking was super, super popular. And if somebody found a cross-site scripting vulnerability on your website, you would start, or at least all of your visitors would start, mining cryptocurrency and sending it to these attackers. Now, another really popular one came from a collective that we refer to as MageCart. Now, MageCart did the same thing. They found a way to get JavaScript into your site that didn't belong there. And when they got this JavaScript into your site, it was just a tiny little file that would simply bind to all of the key presses and then Ajax them out the back. It was a simple keylogger. The site would load, the script would load, and as your users are sat there typing, all of their keystrokes are being logged and sent to the attackers. And MageCart focused very specifically on sites that have an e-commerce component, some kind of online payment. So you would go to the payment page, and what do you type in on payment pages? Right, full 16-digit card number, expiry date, security code, your address, your name, everything. And they would be siphoning all of this data off from your site because they found a way to get a simple few lines of JavaScript on the page. Now, these are two pretty notable examples of the kind of things that would go wrong and the kind of things that you might want to prevent from happening. Now, to prevent this from happening, there is a mechanism that you can use called content security policy. And this is a super powerful application security mechanism that would allow you to stop the attacks I just mentioned and a lot more things from happening. And you write a content security policy for your site and then simply return it to the client as a HTTP response header with the page. Right, so you write the security policy, this is what's supposed to happen on my page, you stick it in the header, and you send it to the client with the page. And then the client will simply enforce the policy. Right, these are the things that are supposed to happen on your site, I will only let these things happen. Now, as long as your policy doesn't include things like cryptojacking or malware, then the browser will stop those things from happening. So you could stop bad stuff from happening. Now, most people want to control JavaScript with content security policy because it's the most powerful type of content on the page. And what you would do is you would define your content security policy header. You would issue what we call the script source directive. I want to control where script is going to come from on my page. And you would say self. You might load some JavaScript files from yourself, from your own domain. And you might load, let's say, jQuery from the jQuery CDN. And now, if we saw the script tag just a moment ago, if the browser sees that in the page, it would look at the source attribute on that script tag and say, evil.com. Well, evil.com is not in the allowed list. So we will block this script tag from loading. And the attack is completely neutralized. That script tag will not be run on the page. And this is all you would have to do to stop it. And that's super, super powerful. Now, you can control all of the other types of content that you may have on your page. You can control styles, and you can control images. Child sources, things like iframes and other nested browsing contexts. But you can even control where data goes to. Things like connect sources, where can the page send data? We also have form action, where can we send data out? So you can control where stuff comes in and where stuff goes out. You can take full control of absolutely everything with CSP. Now, the problem is, this is done on the client. So let's say my website had that script tag that we just looked at. I've sent this policy to your browser. You've come to my site. The evil script tag has been blocked. It's not going to run. And that's great, because you are now protected. You're not going to have your credit cards or your names or your passwords stolen. But I don't know, right? It happened on your client. It happened in your browser. And I don't have any knowledge that that happened. But content security policy has a way to fix that, because I need to know about the issue to be able to fix the issue. So with content security policy, there is one final feature that you can enable, and it's called the Report URI directive. And this is where you say to the browser, look, if something goes wrong, if you block something based on this policy, what we call a violation of the policy, I want you to send a violation report here. I want you to tell me, hey, I came to your site, you said this should happen, but also this other thing happened, and I stopped it. And that will now give me the ability as a site operator to go to my site and actually fix it. So this was the feature that I wanted to leverage all of those years ago. And I was like, wow, that sounds pretty cool. Like, I would love to know about this. So I went on Google, I tried to find a service that did it, and I couldn't find a service that did it. I spent like 5 minutes on Google. Definitely doesn't exist. So I built one. I was like, right, well, you know, how hard can this be? Famous last words. Like, how hard can this be, right? I'll just build a service to ingest some JSON. And hence, like, the name of the company that I built was Report URI, because I'm bad at naming things. So I just borrowed the name from the standard. So I built a company, well, I built a project originally, actually, to ingest these reports, these violation reports, for myself. Because they simply come in as a JSON payload in a post request, right? It's not too difficult, not too complicated, I thought. I was like, great, stand up an endpoint, you have to receive these post requests, parse a little bit of JSON, and I can start to find out about interesting things or bad things that are happening on my site. So you would visit my site, something would happen in breach of the policy, a violation, and then your client would send the post with this JSON payload. It tells you, what page was I on? What was violated? The script source. It gives a copy of the original policy, because you may be referring to this later, so you want to know, well, what was the client working with at the time? So you get the original policy, and it will tell you what was blocked, among several other pieces of information in there. So now, if I were to receive this, I'd look at this and be like, whoa, I need to go fix this right now, because apparently there's a script tag on my page loading from evil.com called keylogger.js. I have a new JavaScript dependency that I didn't ask for. And this was the JSON payload that the service was built to ingest. Now, when I started it and it was just me, it was in like the hundreds a month, right? I would get hundreds of these payloads per month. Super, super easy. But I actually got some useful information from it. So I was like, OK, I'll build a nice front end and I'll put it online. And I'm like, hey, I built this free tool. People can check it out. You can use it if you find it interesting or useful. Now, when I actually launched it publicly, the kind of first month was in 2015, when it was actually open and anybody, apart from people that I knew, could go and register and use this kind of tool or product, if you want to call it that. And by the end of the first month, we'd done 1 million JSON payloads, right? I was like, wow, like 1 million pieces of telemetry came in. I was like, this is amazing. And it's just running on one little server in DigitalOcean. It's like $20 a month or something. This is nice and easy. But then a couple of other people were like, hey, actually, yeah, we got some useful telemetry from this. People should use this. This would be really good. So time goes forwards. And at one point in 2016, we hit a marker where we were doing 1 million of those reports per day. I was like, wow, this is scaling up. But 1 million requests a day, right, is still kind of within the realms of being reasonable. And I could just add more cloud, right? Like, we've got a problem, got more data, add more cloud. Costs a little bit more money, but we can just throw money at the problem because the amount of money is still small. We get to 2018, that was the next marker for me, which was when we were doing 1 million of these an hour. Now, they're all JSON posts. They have all got database activity. They've all got something to be done with them. This isn't a GET request from cache. It's a POST request with a JSON payload that you must do something with. And I'm like, OK, it's kind of getting a little busy now. And then we got to 2021, when we hit the next marker. And I was like, when I first kind of started to delve into this problem, I was like, OK, how long does it take us to do 1 million reports? On average, throughout a 24-hour period, we would do it every 15.4 seconds. We would process 1 million JSON payloads. And then it just kept getting worse and worse. So now we can, at peak in America time, because we get like the vast majority of our reports in America time, we do around about 64,000 a second. So if America's awake and on the internet, we'll be doing 64,000 JSON payloads a second. Now, there's only so far you can get through this problem by just adding more cloud, right? Adding more cloud makes it more expensive. And I had to kind of get a bit smarter about how we're doing things. And there were several things that I did along the way to try and ease our processing burden. So all of the different browsers and clients out there slightly disagree on how the JSON should be structured, right? It's like there's a specification, but that doesn't matter. So we normalize really, really hard on the way in. Some browsers will include querying parameters, some won't. There's loads of differences. So we try and flatten them down as much as possible. We have a nice Redis cache on the way in, and we normalize them hard on the front and then deduplicate them on insertion into the cache. We looked at how our users were querying the data and thinking like, well, how can we better store it to then better query it? Because querying over the data was becoming really, really difficult. When you've got terabytes and terabytes of JSON in the database, it becomes hard to run queries. So based on how people were querying in the UI, we now store the reports in little time series buckets for the hour, the day, and the month, because they were the most popular query formats. Deduplication, again, this was slightly further than normalizing the JSON. Some browsers would include fields that are not in the standard, like extra information to try and be helpful, I guess. But these were cluttering up the UI, because you would have multiple different reports in the UI that essentially track back to the same problem. So we would try and flatten those down also. Spam reports and noise. Anyone here use browser extensions? Right? Like loads of people, half people. You put a browser extension on the page, and you want a browser extension to change the font. Right? The browser extension goes in the browser. The page loads, and it's like, no, we don't want that font. We want this font. And it shoves a new font in the page. And the font violates the policy because it's loading from somewhere that was not allowed. If you violate the policy, a report gets sent. So popular browser extensions can trigger huge quantities of data to be sent. So we've now got some really good methods for identifying those and just discarding them. We don't need them. Users don't need them. And then we don't have to process them. But eventually, we kind of hit our final problem, which was too much data on disk, right? It was just too much JSON in the database. So we introduced a 90-day retention policy, right? Once a report gets 90 days or older, we just chop it off the back. So you can only ever look at a sliding window of the last 90 days. That allowed us to obviously get rid of the vast majority of data on disk, hugely reduce our overheads. But this one actually came with it one of the biggest problems. Now, one of the most common things that people want to know, if a report comes in, they want to be able to answer this question. Have we seen this before? Like if a report comes in and it is the first time something is being reported to you, you're probably more interested in it than, if this is like the 47,000th time this has been reported, you're like, yeah, OK, we know about this and we're dealing with it. So one of the features that we really wanted was to be able to alert people, this is like a brand new report. You've never seen this before. It's never been reported before. Now, OK, yeah, there's loads of data in the database. We could query over and say, like, is this thing in there? But then you hit the 90-day retention policy. And you're like, well, actually, all we can say is, have we seen this before in the last 90 days, right? Because all of the data beyond 90 days has fallen off the back and is now gone. So even answering this simple question, have we seen this before? Number one, querying over huge quantities of data is really, really difficult. When the reports are coming in the tens of thousands a second, that's really hard. and also 90-day limit anyway, so it's not actually answering the question. And these two major problems were the ones that I set out to solve, answering this one question. And it sounds so simple, and I was like, oh, this will be great, we'll just set up some alerting. And then I actually looked at the scale and the volume and thought, yeah, we can't query the database like that tens of thousands of times a second to say, have we ever seen this thing before? So I was like, how can we do this efficiently? How can we do this in an achievable way? And I started looking at something called probabilistic data structures. Now, a Bloom filter is a probabilistic data structure. And in order to explain it, I'm going to take you through this example of a rather simple Bloom filter, but it demonstrates all of the qualities. Now, a Bloom filter, as you can just see here, is an array of bits, all initialized to 0. So the width of the filter W is 10. In this case, we have got 10 bits. And when we insert an item into the filter, you need to set a number of bits in order to reflect that item. So we've got 2 here, k equals 2. So we use 2 hash functions to set bits in the array to say, we've seen this item, we're going to set these 2 bits. So we'll take a look at what it looks like. We're going to do this using h1 and h2 because we've got k equals 2, 2 hash functions, 2 bits to set. The only requirement for these hash functions, you want them to be as fast as possible, but you need them to be what's called pairwise independent, which means if you hash the same item with hash function 1 and 2, they will always generate a different index in the array. That's all pairwise independent means. So let's do it. Let's take item A. A report has come in. We'll just refer to it as item A. It's a JSON payload, and we're going to take the first hash function 1. We're going to hash item A, and then we modulus it with the width of the array to give us an index that's in range, and it gives us index 2. Then you take the second hash function 2. You hash the item, mod it with the width, and it gives us 4. Now we've received this item, it's come in, and we set the bits in the array. So we just set the bit there, we set the bit there. This now indicates we have seen item A, and we have inserted it into the Bloom filter. And this is now what we do for reports that are coming in, for reports that we're processing. The next report comes in, item B. OK, we've now processed it. We need to set it in the array to say we've seen it. We need to set it in the filter. So we hash it with hash function 1, gives us index 6, hash function 2, gives us 9. Yeah?
What if the modulus is the same? They're different, the outputs are different, but they both, the modulus of the 2 is the same.
So you mean for like a collision?
A collision with the modulus rather than the actual output. So things like your modulo 10, so both 20 and 30, for example, would they're the same value.
But because the width is always the same. Oh, so the only way that you would realistically be able to do that is if you wrapped over multiple times, which with a realistic width you would never be able to achieve. So you are correct in my example, but in a realistic scenario, the width, you'll see in a minute, I'll give you some realistic numbers, the width would be too large. And I'll explain that at the end, actually, because we have a Q&A section. But it's a really good point. This is just because of a poor, short array for the example. But for now, we've got bit 6 and bit 9 set. So this now stores the information that we've seen item A and item B. So if we now look at item C, we've got the Bloom filter in front of us. We want to query, item C comes in, have we seen this thing before? We now want to query the filter. We don't want to just insert something into it. We want to be able to query it. So to query item C, to say, have we ever seen this thing before, we simply do the same, but look up the bits. So we hash it with hash function 1, which gives us index 4, which is set. And then we hash it with hash function 2, which gives us 7. And we can see the bit index 7 is not set. So we can now say we have never seen this item before. Because if we had seen this item before, we would have done this process, and the bit at 7 would be set. So we can say definitively, 100%, we have never seen this item before. So this is how a Bloom filter works in principle, with a short, simple example, but this is how it works. But they do have one drawback. There is one thing that we always have to consider with a Bloom filter. If we query item A, an item that we have seen, we can say, if you remember from a few slides ago, we set the index 2 and 4. So we could query item A, and we could say, yeah, we've seen this before, right? Like we set those 2 bits earlier, 2 and 4, they're both 1, we've seen the item. But then we query another item. Now this is item D. We've never seen item D before. I haven't inserted it yet, but we're going to query item D. Hash function 1 gives us the index of 4, and hash function 2 gives us the index of 9, which are both set. Now, index 4 was set when we inserted item A, and index 9 was set when we inserted item B. So now the filter is going to tell us that we have seen this item before. But actually, that's not what it's telling us, because it is a probabilistic data structure. Bloom filters can only give you a definitive on the negative. They can say, no, this has not been inserted. And that is with 100% accuracy. But when they say, yes, this item has been inserted previously, they're doing it with a probability that this could be a false positive because of collisions with other bits that have already been set. And this is the nature of a probabilistic data structure. You can ask them a question. Was this item in the set of all inserted items? And it can tell you, definitely no. And that is 100%. If the filter says you've not seen it, you've not seen it. However, if it says yes, caveat, with a probability that this is a false positive. Now, you can control the false positive probability. You can have a relatively large amount of control over that. And you control that when you're setting up the filter. So now, if we take a look at setting up the Bloom filter, there's obviously a few different characteristics that you can control. So if we take a look, I had a very small width of 10, but obviously in real scenarios, you would have something much larger. We also have number of items that you expect to insert. You need to have at least a rough idea on how many things are you going to put in the filter, because this will impact the size. You can then also derive k, which is basically the number of bits that you're going to set for each item that is present in the filter. And then finally, you can control p, the probability that there will be a false positive. Now, it's relatively easy to calculate these values. You can kind of think of it like you get to pick two, and then the other ones are derived for you. So for us, we needed to get some kind of idea, like how many items are we ever going to insert? This was a particularly difficult one for us. But whichever one you pick, whichever item you want to control here, you simply calculate the others. Now, there's Bloom filter calculators online. You don't need to learn any of this. But just as a general point, you can see, for example, if you were deriving the width, then you can see we use the number of items and the probability of false positive. Obviously, a larger number of items equals larger width. If you want a lower probability of false positive, you need a larger width again. Same for the number of items going in there. More items equals more width equals more bits set per item. So they're all derived from each other. And you would just pick the couple that mean the most to you. So for us, we went for the width, and I wanted to control the probability of false positive because I wanted to keep that kind of low. So those are the two items that I wanted to exert control over, and then the other two were defined for me. So to calculate the width, I was like, OK, well, I'm going to assume over time we're going to insert 7 billion items into this filter. Now, remember, this is 7 billion distinct items. I know we're processing tens of thousands of reports a second, but significant quantities of them are duplicates. So this is a projection over time for distinct reports that will be put into the filter. But we're going to put somewhere in the region of 7 billion of these reports into the filter. And this is the probability of false positive that I would like to have. And from there, it's a simple case of just calculating. You substitute in the values, and then you can get to the size of your filter. Now, it's kind of pretty big, and then it's also not really that big at all. When you think about what we're going to do with this, so we're hosted in DigitalOcean, and we ended up spinning up a dedicated Redis cache for this, and it costs a few dollars a month to have a machine with like 16 gig of RAM, right? It's really not a big deal, super, super easy to do this. So that was going to be the size requirement of our filter. Then, of course, we needed to calculate k. So we now have our defined width. We know the number of items going in there. We need to figure out k. How many bits are we going to set in the array for each item? And it came out at 7. In order to hit our false positive probability, we need to rely on the accuracy of 7 bits. So we will be setting 7. And this was it. This is what we did. Now, if you don't want to do all the math yourself, like I said, there's some really good Bloom filter calculators online. Just Google them. There's plenty of them. And we use this in production. We set this up, 8.5 gig approximately. Relatively low-powered Redis cache, actually. So Redis has really good support for Bloom filters and the other data structures I'm going to talk about. And now we can take all of our inbound reports in our processing pipeline, and first thing that we do is query them against the filter. As soon as a report comes in, brand new report, it's been deduplicated, it's been normalized. Have we seen this thing before? Now, if that filter comes back and says no, we know for sure, 100%, we've never seen this thing before. And if it says yes, we're like, OK, there is a probability here that this is a false positive, and it's something that we've never seen before. But we were looking for that definitive no. Like, how quickly can we get the no and send an alert? And that's what the filter tells us. It gives us a guaranteed no. So this works for us. And as long as you can kind of live with the drawbacks of probabilistic data structures like that false positive on the yes, then they can work really, really well. So I went out and I dug out some other examples of the use of Bloom filters in real-life scenarios, so maybe they can relate better. Now, one of the ones that I liked was a white paper that came from a company called Akamai. Now, Akamai are a CDN provider, so they reverse proxy their sites. You put your site behind the CDN, and they serve all of your requests and cache assets and things for you. And what they found was they were looking at their edge caches, so they've got their data centers all around the world, and they have edge caches with all of their customers' files that they've cached, and then they would serve out. And they were like, OK, well, we have a huge amount of data in the cache, but is all of it really being used? Are these like highly requested files that we need to cache? And they're like, well, we'd like to only cache a file if it's a certain kind of like popularity, a certain number of requests. If it's a file that's requested super infrequently, we don't want to cache it because it's just going to sit in the cache and then expire, and we cached it all that time for nothing. So they set up a Bloom filter in front of their edge cache. And what they would do when a request came in for a file, if the file is not in the cache and they're contemplating going back to the origin server to fetch it, they would query the Bloom filter and say, has this file been requested before? Now, whilst they're doing this, the Bloom filter will obviously say, no, this has never been requested before because it's the first time. They would fetch the file from the origin and serve it to the client, but they wouldn't cache it because it's never been asked for before. It's like, no one's ever asked for this file, so we're not going to cache it. And then they'll set the bits in the filter. And then when the second or any subsequent request for the file comes in, they query the filter and say, yes, this has been requested before. So that time when they fetch it from the origin and serve it to the client, they drop it in the cache on the second request. And this helped them eliminate what they refer to in the paper as one-hit wonders, a file that is requested once and then cached, and then sits in the cache until expiration and nobody ever asks for it again. And they managed to reduce the size of their cache by around 74% by eliminating one-hit wonders. So they removed 3/4 of the data that they were caching for absolutely no reason, using a simple Bloom filter on the way in. I found another one. This one's particularly interesting because this one's up my street of security. Now, Google Safe Browsing is a really, really good idea. And as I start to explain it, in the middle it sounds like a terrible idea. So when you're browsing websites, you want to know, I'm about to visit this URL. Is this URL malicious? Right? Like, I would love to know before I go to any URL in my browser, is there something malicious at the other side? Now, Google Safe Browsing is a collection of known malicious URLs. They have a huge data set that comes from sources all over the web. So you're sat there on your browser, and I want to go to this URL, and I want to know, is this URL malicious? So what your device could do, what your browser could do, is take that URL and send it off to Google in a request and say, hey, is this URL malicious? I'm about to go there. Now, it sounds like a good idea because they'll be able to tell you yes or no, it's malicious. But then it sounds like a really bad idea because that sounds like some very invasive and privacy-concerning tracking. I don't want to be shipping all of the URLs that I visit off to some external API to make sure that they're OK. So how do we deal with it? Well, they built a Bloom filter. So on the Google server with their ginormous list of URLs that are malicious, they insert them into a Bloom filter, literally a couple of megabytes. They ship it down to the client, and then when I open any page, if you're using Chrome or Firefox or anything, every time you open a URL, every time you do a navigation, it queries the Bloom filter locally and says, is this URL in the set of all items? Is this URL in the list of all malicious URLs? And it asks that question and does the query locally. So now we're not hitting an API and being tracked and having our privacy invaded. You can do that locally. Now, what can the Bloom filter tell you? Definitely no. Great. Navigate, off we go. No problem, it's not malicious. But then the Bloom filter can say yes with the probability of false positive. So in those scenarios, that is when your client will then reach out to the API. Now, it still sounds like a bad idea, but there is a but. they use something called k-anonymity to query the API. It's not the focus of the talk, but it's super, super cool. You can query an API for something without telling the API what you're querying for. And that's what they use. So you can take the URL, query the URL against the API, and the API doesn't learn what the URL is. It's called k-anonymity. Check it out, it's really awesome. But the point is, they went from querying every URL you visit to only the ones where the Bloom filter says yes. So they took it from basically all requests to basically no requests, using a simple Bloom filter on the client. Now, have you ever been to a news website and they say to you like, hey, you've read this article before, so we're going to give you this list of new articles, right? It says new articles, like articles you've not read. Medium does this. You go to Medium and they're like new articles, things that you have not read. And I thought to myself, well, how do they keep track of that, right? Like, how do they know? Do they just have like a database of all the articles that I've read? And it turns out it's not a database. It turns out it's a Bloom filter. When you read an article, they set the URL of the article in the filter, and then when they get out the stream of new articles, they query them against your Bloom filter to say, is it in there? Has Scott read this before? And if it says yes, they're like, right, throw that one out, it's not a new article. And here is the new list. I was like, okay, it feels a tiny bit overkill, but it works. It is the same principle. So you can now go to Medium, read an article, and know that this is being done by setting bits in a Bloom filter. Now, we do use this at Report URI. This Bloom filter is, yeah, okay, I admit 8.5 gigs of RAM, 9 gigs of RAM. It's quite a bit, but for what it does, it's basically nothing. Right, like the Redis cache we spun up on DigitalOcean is $50 a month. And we're pushing like 50, 60,000 reports a second at peak, like much lower in the nighttime. But at peak, we're pushing like 50, 60,000 requests a second against the cache. And it's basically free. All in memory. The hash functions are super, super cheap. We're just checking our 7-bit set. Right, it's virtually free. Now, there are other data structures built on top of Bloom filters. We have other probabilistic data structures. So one of the first ones is something called a counting Bloom filter, right? Saying yes or no, have I seen this item before is okay, but what about how many times have I seen this item before? So it's the same principle. It is a one-dimensional array, a filter, as we refer to it. It's the same probabilistic nature, obviously because a Bloom filter is the base data structure here. The only thing is, we're now counting a threshold. So instead of just setting the bit for the presence and setting 7 bits, you would take the counter at those 7 locations and increment them. So we've seen this report one more time, increment those counters. Now, of course, because of the collisions with other items, we can see counters over-increased beyond the true number. And that is why the item is possibly greater than equal to the threshold. But what you can say, you've got the definite negative. This item is definitely not less seen than this number. So it's the same probabilistic nature, but instead of just setting the bits, we now increment counters instead. What about if you want to delete something? I put this thing in the filter, and now I want to take it out. With the Bloom filter, you cannot do that. If you delete those bits, you break the filter, right? But with the Cuckoo filter, works in exactly the same way, but you can delete items. Slightly higher memory requirement for this one. But you can delete stuff if you need to. We then have what we refer to as a sketch. Now, a sketch is just a 2-dimensional filter, basically, right? We looked at a 1-dimensional filter earlier. A sketch is 2 dimensions. And the count-min sketch allows for frequency analysis on events. If you have a huge data stream, like maybe at peak, 64,000 events a second coming through, and you wanted to do frequency analysis on that data stream, you can do that efficiently with a count-min sketch. Now, again, same probabilistic nature. It's just a 2-dimensional Bloom filter, basically. It allows overcounting, but never undercounting, again, because of the collisions with the increments. And you can define the overcount tolerance. It's the same as controlling the probability in the Bloom filter. Now, I've got an interesting post on count-min sketch, actually, as well, if you want to do some more reading on that with an explanation of how the actual array works in 2 dimensions. But then one that I've done a really kind of extended blog post on was something called TopK. Now, TopK is another data structure that we're currently using in production. And what TopK does, it's built on a 2-dimensional filter, so a sketch. It runs a binary min heap alongside the sketch, and it allows for frequency analysis again. but top K is designed to give you, whereas the count min sketch will give you a count for all items, a top K has way less overheads, but it's only designed to track the top K items. So in our case, it's the top 100. We track our top 100 most common reports. So you can have like top 100, top 50, top whatever you need, but we track the top 100 most common reports every week to see, like, you know, what's going on in the world. Like, what are the big things being reported? Have we got some new incident, some new event? So we stream all of our reports through the top K structure, and at any point, you can take the top 100 from the data stream at that moment in time. So we can simply look at it and say, right now, what are our top 100 items in this data stream based on their frequency? Now, you can query the number out. We don't really use it to count the number. We're actually just looking for basically the top 100. However, because you can define the undercount tolerance and the probability, we can actually use it to get a pretty good grip on the true volume of those reports being reported. So this works. We're currently using this in production as well. I have a really big blog post on this one explaining how it works. And the final one is something called a HyperLogLog. Now, a HyperLogLog is... we use it to, like the fancy terminology is, we use it to determine the cardinality of the set, which means basically like how much uniqueness is in the data or how much duplication is in the data. So you take the data stream, you stream it through the HyperLogLog, and it will tell you what is the cardinality of the set. It will count the distinct items that it has seen in the data stream. Now, it does this with massive, massive efficiencies, right? There is like basically zero storage in memory for this thing, and the CPU overhead, the time complexity of doing this is almost zero. If you were to do this in the traditional sense of, you know, inserting them into a database or counting them there, it would come with huge overheads. We can literally stream our entire production data load through the HyperLogLog in Redis, and it's like, yeah, no problem. So we can now count the distinct number of items in the data stream, which was really useful for earlier when I was trying to figure out how wide does the filter need to be for the number of items. So if you don't know what the cardinality of your data is, run it through the HyperLogLog, and it will tell you. So the whole kind of point of all of these things for us was to do this in massively efficient ways. I added cloud for as long as I could, and it just costs more money, right? Like more cloud equals more cost. And for what was a side project at the time, I needed to do this in way more efficient ways. Now, I wanted to leave plenty of time for questions on this one, and I now want to open this up to the audience. I appreciate it's the last talk, and you know it's like, what, 5:30 or something, 6 p.m.? But I did leave lots of time for questions on this, and I'd be happy to loop back to the question at the front there now that we have a little bit of time to do that. So you were saying, if I remember correctly, please correct me if I'm wrong, if we modulus it with the width, both of the hash indexes could wrap around and potentially collide with each other. Yeah, probably with a width of 10, but not with a width of like, I can't even remember what our width was, like 27 million or something. Like, so essentially, yeah, that was just a like a byproduct of me using a really, really small demo. So let's open it up to questions. There must be some questions here. Yes, go ahead.
Presumably, again, maybe you just answered this with
No, it's okay, go ahead.
presumably after a certain number of cycles, all those zeros have turned into 1. Or just,
Yeah, no.
does that not happen?
No, it does. So I'll repeat the question for the audience, and I'll go back to a slide to help me answer that question. So the question there was basically, you know, at some point in the future, correct me if I'm wrong, at some point in the future, you're essentially going to have all of these bits in the array set, right? Is that, did I? So yeah. So this is one of the problems that we have with Bloom filters. If we overpopulate the filter, they kind of become useless, right? So imagine my terrible example with width of 10. I would probably only have to set a few more items, and every single bit in here would be 1. And then the filter is utterly useless. So the number of items that you set in the filter is highly relevant. So when you set n, you have to be at least reasonably confident you're going to be somewhat close to that. So you can't set n and then insert like 10 times n, because the filter will be overpopulated. Now, the other kind of interesting thing there is, obviously, the number of items I set in this filter will impact the probability of false positive. As I set more items, more bits are set, more false positives. Between having nothing set and having the full population set, your probability of false positive actually goes from 0 to the expected probability of false positive. So you don't actually, you get better than the defined probability at every point before you're at population. So technically, it's getting worse and worse and worse until it hits where you are. But then, if you overpopulate the filter, the probability of false positive continues to get worse. But then it increases at an exponential rate. So you don't have to go far over the population to start having a really significant impact on the rate of false positives. But yeah, you've got to have a good control on n. Good question. Yeah? So at that point, what do you do? Like, what happens if you overpopulate it? Well, this is a problem because you can't, there's really nothing that you could do. If you like wipe the filter and set it back to the beginning and say, okay, we want to do this again, but n equals like 10 billion, you would need the original data set to set all of the items back in the new filter. And one of the problems that we set out to solve was our 90-day retention problem, to answer the question for basically data that we've deleted. So this is not the sole mechanism that we currently depend upon. If we get the definitive no, we've not seen this before, it's used to short-circuit the alerting process and just immediately kick that off. So we don't have to then go and query over like terabytes and terabytes of JSON on disk. So yeah, like you need to think, you know, like if you become fully dependent on this as the sole mechanism, you need to be aware of all of the drawbacks. If you overpopulate it, you can't ever get back unless you've got the original data set. Now, if you have the original data set, then yeah, you can absolutely do this. I built a Bloom filter. Is anyone familiar with Troy Hunt's Poem passwords? So a really common use case for Bloom filters is something like that. So I took Poem passwords, and I was like, right, okay, you've got to query against the API. There's like external network comms, delays. What if we just took like the Poem passwords data set, put it in a Bloom filter? I have a blog post on it. I built one. You can query against the filter locally. Is this password in the data set? Definitely no. Then the user can use it. Is this password in the data set? Maybe yes. Then we query the API, right? So we've cut down the amount of external API traffic by a significant margin with a really, really small Bloom filter. And it's those kinds of scenarios where they're super helpful, where they help you cut down massive overheads in most cases, right? They're not perfect and they won't solve all overheads, but they keep allowing us to cut really significant amounts of work out a lot of the time. There was another, yes?
This Bloom filter is effectively a massive bits array.
Yes.
Millions of bits, and that's held in memory. Is that updated on the way in with requests in real time? And if so, is that computationally expensive?
Okay, so the question there, is this essentially just an enormous bit array? Yes, absolutely. Is it updated on the fly on the way in? Yes, so we will query it first, and then depending on the result of the query, if we've not seen it, then we will set it. But if we query it and we've seen it, we don't have any other interactions with the array. Now, in terms of reading the bits and setting the bits, it's so lightweight, right? Like we do this at scale, and the Redis cache is just like sat chilling out, like taking its time. And it's not a problem at all. We would have to be doing significantly more volume. The network latency to the Redis cache, which is on the local network, is like a gazillion times more expensive than the operation in Redis. So if anything, we just need to move the Redis cache closer if we can. That's where the cost is. Did that cover everything?
Yeah.
Okay, more questions? Yes, just here. Yeah, no, go ahead.
Given the idea of when the array gets full of all the bits are turned
Yes.
on, and you've got a retention policy of 3 months,
Mm-hmm.
couldn't you have several of these running in parallel? And so as something comes in, you put it in multiple Bloom filters. One of them's 3 months old, one of them's 2 months and 2 weeks old.
Okay, yeah.
And so when you blow that data up, you blow up the Bloom filter that went with it, and you can just go
Okay.
a week at a time or whatever, and then like having multiple database indexes.
Yes. So the question there was basically like, because we have particularly a 90-day retention policy, like could we run, essentially like what you're referring to is what we call temporal sharding, which is like we would shard the filter based on time, and like everything in this 90-day window would go into this filter, and then the next 90-day window. So yeah, temporal sharding is a thing. Right now, especially because I've created a filter so large for hopefully like all reports for it's future Scott's problem, not current Scott's problem when it gets full. Future Scott's going to hate me, but yeah, like you could do sharding based on time as well. I can't see any reason why that wouldn't work. We have a very similar concept, but not quite for the same thing, called cascading Bloom filters. which is where you have like a generally quite low resolution filter to query against to get your quick answer, and then you query against increasingly higher resolution filters to get more definitive answers. So yeah, there's probably a couple of different strategies you could take there to do that. Any more questions? We do have a few minutes left. Oh, there we go. Thank you. And I'll come back.
For a given array, you can know how full it is and therefore how your probability.
Correct. Yeah. So the question there was, given an array of known size, if you look at the number of bits set, can you calculate the population? Yes, you can very accurately estimate the population of the array. If I know the width of the array and the number of bits set per item in the array, you can, with a really high degree of accuracy, count the population. And from the population, you can then calculate what is my current probability false positive. So yeah, you can, if you know the details, you can calculate both of those things with great accuracy. At the back there?
Yeah, to recreate the filter, don't you just need the unique records? You don't need all of them.
Yeah.
You can just store the unique ones for the past 90 days, not everything. So you could recreate it that way.
We could do that. So the question there is, basically, if we wanted to recreate the filter at the current point in time, we only need to store the unique reports that we've seen. So like we could have like some separate table for like unique reports or something. And then we wouldn't need to store the bazillions of duplicates. And then we would be able to rebuild the table at some point in the future. Like, yeah, that would work. We could keep some kind of record of that. In previous iterations, I've spoken to someone and they were like, what about if you just like hash the report? And then you could just store the hash and then perhaps reinsert it in the future. The only problem with the hash is we would reduce the essentially like the character space of the report to generate. If we like SHA-256, then we've only got 256 bits of entropy, and there's still basically zero chance of a collision, actually, I guess. But yeah, like we could just store the report payloads that are unique and be able to rebuild that in the future. And based on, yeah, I mean, there'd actually be really significantly less of them. I've never thought, that's future Scott's problem. I've never thought of a different way to solve that. Like, what if the Redis cache dies and we lose the Bloom filter or something? We're not solely dependent on it right now, so even if it completely goes away, I mean, it would change our reporting time from like a few seconds to a few minutes because we'd have to go down the traditional pipeline. But yeah, that would work. It's a good idea. Any more questions? No? Okay, so yeah, well, thank you very much for joining me. If you do come up with any questions afterwards, feel free to find me. I'm here for the rest of the day. Is anyone going to the event tonight? The NDC, it's like the speaker dinner, but they also open up tickets. No, okay. So if anyone's staying at the NDC hotel, you'll see a lot of us in the bar later. Feel free to come grab me at any time, and thank you very much.